Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 9, Lesson 4, Solving Quadratics Using Inverse Operations. Before we begin, let me just remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes on the top of each one of our worksheets. If you scan those with your smartphone or your tablet, it will take you right to the video that's associated with that lesson. All right, let's begin. So we've solved quadratics so far, equations that have x squareds in them, primarily by using the zero product law. Today, and in some future lessons, we're going to see how to solve them by using inverse operations and sometimes by using completing the square, but that's still to come. Now, let's take a look at the simplest of all types of quadratics. Exercise 1 says solve each of the following equations for all values of x. All values of x. Write your answers in simplest radical form. Also very important. Okay? So, switching back to blue, if I've got an equation x squared equals 16, then it should be clear to me that there are two numbers that I can square to get 16. 4 and negative 4, right? That's it. Now, what a lot of teachers will show students is that the inverse of squaring is square rooting. Now, that's fine. That means that when you kind of cancel these two out, if you will, you get the square root of 16. One of the things that's very problematic about that, though, is it would only result in one answer, which is 4. Right? So what I tell my students, and what pretty much all teachers tell the students, is that when you take the square root of both sides of an equation, you always introduce a plus or minus. So we get x equals plus or minus the square root of 16, which means x is plus or minus 4. Watch how that works in letter B. Okay, we have x squared equals 100. Let me rewrite it here so I have a little bit more room. To get rid of the squaring, we take the square root of both sides, and we'll get x equals plus or minus the square root of 100. But 100 is a perfect square, so we get plus or minus 10. And that makes sense, right? Because if we square 10, 10 times 10, we get 100. And if we square negative 10 times negative 10, we get 100. Now that's important. You might just say, hey, well, why not just write down 10 and write down negative 10? And I can't disagree with you. That works. But when we get a situation like letter C, x squared equals 20, you see, 20 is not a nice perfect square. Right? So when we take the square root of both sides, that gets a little bit confusing. What is the square root of 20? Right? Well, that's where the simplest radical form comes in. Remember how we do that, right? We find the largest perfect square that goes into 20, that happens to be 4. And we can break 20 up then into the square root of 4 times the square root of 5. All right, take the square root of 4 and we get 2. Don't lose that plus and minus. And we get plus or minus 2 times the square root of 5. Now, really, I do want to emphasize there are two answers there. All right, and those two answers happen to be positive 2 times the square root of 5 and negative 2 times the square root of 5, right? Those are those two answers. All right. Now, not always, but often, when we solve equations that have x squareds in them, we end up having two solutions. In fact, as you move on in math, what you'll find out is that the maximum number of real solutions that you can have will always correspond to the highest power. So an equation that had an x cubed in it as its highest power could have 3 real solutions. Something with an x to the 4th could have 4. Notice I have to keep saying could have that many, because you can have quadratics that have only one real solution, and you can even have quadratics with no real solutions at all. We'll see that in a future lesson. But for right now, we need to build off of this, all right, by coming up with more complex quadratics. All right, so pause the video now and write down anything you need to, and then we'll clear out the text. Okay, here it goes. All right, let's move on to the next problem. Okay, exercise 2. Solve each of the following equations for all values of x, by using inverse operations. In each case, your final answers will be rational numbers. Rational. Now, remember what that means. No irrational numbers, so no square roots of non-perfect squares. Now, what we want to do, though, is use inverses in the opposite order in which they happened, right? So take a look at this, right? The first thing that happened was squaring x. And I'm going to only write this out first. We squared x, then we multiplied by 2, and then we added 10. All right? So we will undo that in this order. Right? Let me go to red. Right? We will undo that by subtracting, undo that by dividing, and undo that by square rooting. Okay? So let's do it. Let me take my problem and put it down here. 2x squared plus 10 is equal to 28. First thing I'm going to do is use the additive property of equality to subtract 10 from both sides. That's going to get me 2x squared is equal to 18. Then I can use the multiplicative property and divide both sides by 2. That's going to get me x squared equals 9. And really, at that stage, I'm back to where I was in exercise 1. Now I can take the square root of both sides, and I just have to remember to put a plus or minus in there, and I'll get plus or minus 3. All right, so either one of those answers will solve this problem. Okay, so let's do the same thing in this problem. What did we do? We squared x, we divided by 2, and then we subtracted 5, right? Order of operations. So I'm going to add 5 to both sides, giving me x squared divided by 2 is equal to 8. Then I'm going to undo that division by multiplying both sides by 2, giving me x squared is equal to 16. And again, I'm back to where I was previously. I will now undo the squaring by taking the square root of both sides, have to introduce that plus minus, and x will be plus or minus 4. All right, so as long as we have an x squared and not an x to the first, right, then we can solve these not by using the zero product law, but by simply undoing what has been done to x, which is why it is the most powerful equation solving technique, saying, okay, I've got the input variable just once, the x or the t or whatever, and I will undo what has been done to it. And that will always work as long as it shows up only once. Okay, so I'm going to clear out the text. Why don't you go ahead and pause the video and write down anything you need to. Okay, let's keep going. All right, now we're still in exercise 2, but we're going to ramp it up a little bit. We're going to change them a bit. So let's analyze that order of operations piece again. All right, take a look at this equation. The first thing that was done to x here was we subtracted 2. The second thing that we did was we squared. All right, therefore, when we undo what's happened, this will actually occur first, and this will occur second. Right? That's kind of important. You don't want to just start to go, what a lot of students will do, not a lot, but some students will do is they'll add 2 to both sides. Then they'll take the square root. Nah, you have to undo that squaring first because it was the last thing that occurred. So let me write it down here. All right, let's take the square root of both sides. Now this is going to get a little tricky here. We have x minus 2 here, and then we'll have plus or minus the square root of 25 here, which means we'll have x minus 2 equals plus or minus 5. Now what in the world do we do with this? Well, kind of like the zero product law, this really means we have 2 equations now to solve. We have x minus 2 equals negative 5, and we have x minus 2 equals positive 5. We can now solve this one by adding 2 to both sides and gets me x equals negative 3. And we can solve this one by adding 2 to both sides and getting x equals positive 7. There we go. Right? The key here is understanding your order of operations. So let's lay that out one more time in the most complicated one that we have right here. Let's take a look. The first thing that was done to x was we added 5. The second thing that we did is we squared, right? The third thing that we did was we multiplied by 2. And the fourth thing that we did was we subtracted that 50, right? See it? We added 5, then we squared, then we multiplied by 2, then we subtracted the 50. Order of operations, right? So the first thing that we will undo is adding the 50, or we'll add the 50. Then we'll divide by 2, then we'll take the square root, and then we'll subtract 5. All right, let's do it. I'm going to rewrite the problem down here. 2 times x plus 5 squared minus 50 equals 150. Let's add 50 to both sides. That gives me 2 times x plus 5 quantity squared equals 200. That almost looks like an equals. There it is. Let's now divide both sides by 2. That gives me x plus 5 quantity squared equals 100. Let's take the square root of both sides. That's going to give me x plus 5 equals. Now I'm going to do this all at once. Plus or minus 10. Okay, remember the plus minus. That gives me x plus 5 equals negative 10. And x plus 5 equals positive 10. Subtract 5 from both sides. We'll get x equals negative 15. Subtract 5 from both sides. And we'll get x equals 5. And that's it. Whew, made my hands sore, but that's it. So if x shows up only once in a quadratic, just once, then no zero product law necessary. All you have to do is identify step by step what's happened to x, and then reverse it. All right? So write down anything you need to, and then we're clearing out the text. All right, let's do it. So all of those problems were kind of nice because in each case the answers turned out to be rational numbers, meaning that when we took the square root, we were always ending up taking the square root of a perfect square. Let's take a look at them when they don't turn out that nice. All right? Solve each of the following quadratic expressions using inverse operations. Express all of your answers in simplest radical form. That is such a buzz phrase. Now again, depending on what state you're taking Common Core Algebra 1 in, you may never see that. You may never see that piece of instruction. New York State definitely expects you to be able to do that, but other states may not. And I know that seems a little bit weird, given that it's actually kind of a challenging procedure. Anyway, let's jump right into it. Okay, just like before though, forget about simplest radical form. We've squared x, we've multiplied by 5, we've subtracted 2, and we got 38. So the first thing I'm going to do is add 2 to both sides to get rid of that subtraction. That was the last thing that happened, so it's the first thing that I will undo. Now I will undo that multiplication by 5, and I'll get x squared is equal to 8. Now, it was nice when x squared was 9 or 16 or 100, but 8's not so nice. But it doesn't make any difference to me at this stage. I'm still going to take the square root of both sides. I'm going to still introduce a plus minus. The big difference is now I have to deal with simplifying this. I'll do that by finding the biggest perfect square that goes into 8. That happens to be my favorite, which is 4. All right, the square root of 4 is 2. That I can't do anything with. The square root of 2 I have to leave. So I get x equals plus or minus 2 times the square root of 2. All right, simple enough. Let's take a look at one that's a little bit more complicated. Here we've subtracted 3, then we've squared, then we've added 10 and gotten 38 because I really love the number 38 apparently. All right, so we are going to begin by subtracting 10 from both sides. Get rid of that addition by 10. All right, and we get this. Now at this point we have to get rid of the squaring, and that's a little bit unfortunate, and I'll show you why. Okay, so at this point the square root of 28, I have to introduce a plus or minus, okay? And I also want to simplify this thing, okay? So how do I simplify it? Well, again, biggest perfect square that goes into 28, not very original here, is 4. I can break down the square root of 28 as the square root of 4 times the square root of 7. I'm just going to keep hanging on to this minus 3 here. The square root of 4, as we just talked about, is 2. And I get this. Now, I'll finish off by adding 3 to both sides. Okay, and I can either write my answer like this, or more commonly, the answer is written like this. Now, let me tell you what's a little bit unfortunate about this. This really looks like you should say, hey, that's 3 plus or minus 2 times root 7. So it almost seems like you should get 5 times root 7, or let's say 1 times root 7. But you can't combine these. So I'm going to write down don't combine. All right. The primary reason you can't combine them is that, if you will, this is an irrational number, right? Because it's a rational times an irrational. And this is a rational number. All right. It's actually very similar to having something like this. If I had 3 plus 2x, I can't make that into 5x. If I have 3 minus 2x, I can't make that into 1x, right? So the root 7 acts very similar to the x, right? We can't combine those terms. There's, by the way, nothing wrong with leaving it this way. I just know how multiple choice answers tend to be left, and that tends to be like this. Don't get me wrong, we're going to be getting a lot more practice with this in the next lesson. Still, why don't you pause the video now, write down anything you need to, and think about these problems. All right, let's clear it out. Okay, let's go on to one that's got a graph involved. This is a fun problem. Exercise 4. Francis graphs the parabola y equals 1/2 x squared minus 6 on the grid below. Okay. He believes that the quadratic has zeros of negative 3.5 and positive 3.5. You know, I mean, if I gave you this graph and I said, hey, what are the zeros? Why would you guess anything else? Now, letter A says, find the zeros of this function in simplest radical form and explain why Francis must be incorrect. So what I'd like you to do right now is pause the video and find the zeros of this parabola in simplest radical form. So do it algebraically, and then we'll come back to it, okay? All right, let's go through it. Well, as we've seen before, anytime you're trying to find the zeros of anything, but especially quadratics, we take the function and we set it equal to 0. So now we have a scenario that we've been dealing with the entire time. What we're going to do is we're going to add 6 to both sides, all right? And we'll get 1/2 x squared is equal to 6. We'll now get rid of that multiplication by 1/2 by multiplying by 2. And we'll get x squared equals 12. And then we'll get rid of that by taking the square root of both sides. So we'll get x equals plus or minus the square root of 12. Now, there's nothing particularly wrong about that, but because 12 is not a perfect square, that this must be an irrational number. Now, it says put it in simplest radical form, so we'll break that up into the square root of 4 times the square root of 3, and that will give us plus or minus 2 root 3. So here are my two zeros. Now, why is Francis incorrect? I mean, why isn't that the same as negative 3.5 and 3.5? These are irrational zeros. But 3.5 and negative 3.5 are rational. All right, so it's interesting. Even though those appear to be negative 3.5 and 3.5, using algebra, we can see that our actual zeros are irrational numbers, right? They're a rational number times an irrational number, so that's an irrational number. Yet negative 3.5 and 3.5, because they've got these terminating non-repeating decimals, right? I'm sorry, terminating / repeating decimals, they're a rational number. Now, Francis was incorrect based on A, but he wasn't too far off. Whoops, there's supposed to be a period there. How can you tell how good his estimate was? So, he's wrong. It's not negative 3.5 and 3.5, but how close was he? Pause the video now and think about how you can show how close he was. All right, well, the easiest way to show is to figure out what the square root of 12 is, right? Or 2 times the square root of 3. So, if we type the square root of 12 or 2 times the square root of 3, it doesn't matter, they're the same number, into our calculator, what we find is the following: 3.4641011615, right? That non-repeating, non-terminating decimal, right? So these are the actual answers, plus or minus this, versus 3.5. And these are very close, very, very close. In fact, if we rounded our irrational answers to the nearest tenth, they would be plus or minus 3.5. But still, the numbers are different because one of them is irrational, or 2 of them are irrational, and 2 of them are rational. Okay, so I'm going to clear this out, copy down anything you need to. All right, let's do it. Okay, let's hit one more problem. Exercise 5 says find the zeros of the function f of x equals x plus 4 squared minus 20 in simplest radical form. Then express them in terms of a decimal rounded to the nearest hundredth. All right, why don't you pause the video now and take a shot at that. All right, well, this is the kind of question that you could very easily find as a free response question on a standardized exam, right? To find these algebraically, we're going to take x plus 4 squared minus 20, and we're going to set it equal to 0. Notice that I've added 4, then squared, then subtracted 20. So I'm going to begin reversing the process by adding 20 to both sides. That will give me x plus 4 squared is equal to positive 20. Now I will take the square root of both sides. Okay, I can't forget to introduce a plus minus. That is so tricky, so tricky. All right, since I first want them in simplest radical form, I will simplify the square root of 20. That's going to be the square root of 4 times the square root of 5. Don't lose your plus minus. And that will be plus or minus 2 root 5. I can finish the problem by subtracting 4 from both sides. And again, I'm going to write it in the way that's most customary, actually putting the negative 4 first, plus or minus 2 root 5. So there are our answers in simplest radical form. Now what we need to do is we need to evaluate them on my calculator. So I'll take my calculator, I'll punch in negative 4 minus 2 times the square root of 5. I'll put enter, and that is going to be negative 8.47 accurate to the nearest hundredth. 2 decimal places, right? 2 decimal places. Then I'll have negative 4 plus 2 times the square root of 5, and that will be 0.47 to the nearest hundredth. By the way, it's not a coincidence that these decimals are the same. But why it works that way, that may wait until Algebra 2. All right, pause the video now and write down anything you need to, and then we're going to finish up the lesson. Okay, scrubbing out the text. Let's finish up. All right, so today we really revisited a topic that we saw a long, long time ago, which is how to solve equations by identifying the order of operations, the order of things that have been done to the input variable, and then reversing them one at a time in the opposite order with the opposite operations. All right. Now, the trickiest part of probably what we did today, and there were quite a few tricky things, was the idea that squaring is what's known as a non-reversible process. So when you square a number and then you go backwards, you introduce 2 things that it could have come from. So I square a number and I get 16. Well, that could have come from positive 4 or negative 4. Therefore, when I take the square root of both sides, when I undo squaring, I have to introduce both the positive and the negative square root. All right, for now I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.